Hello?
Hello all, how are you?
Who is speaking?
This is from lecturer Sri Ramesh Doctor.
No, I am ASHOK ALISHALA. I am colleague of Dr. Ramesh sir. Tell me, today's is my class. Who is this? Who is this speaking? Hello? Who is this? Who is speaking?
Hello.
Video is better than only audio. You connect with only audio. Sir, YouTube live పెట్టిన చూడండి KGC chemistry.
Great. KGC chemistry అనుకుంటా
యూట్యూబ్ లో మన ఛానల్ ఓపెన్ చేయండి అంతే. KGC chemistry KGC ఛానల్ ఓపెన్ చేయండి. యూట్యూబ్ లైవ్ ఒక ఏంటిది అది ఒక టెస్ట్ పెడతా, ఒక ఎక్స్పెరిమెంట్ చేసిన వస్తుందా లేదా చూడండి. రైట్. Good evening, dear students. Only you have eligible for to chart because tell me, Sharanya, chart in the box. Sir, చెప్పండి. Hello. Good evening. Today's our topic is halogen compounds. In this halogen compounds, I divided into the 4 parts, and let us discuss one by one. Don't unmute yourself. If you have any doubts, you can chat in chat box. Okay. I kept open this chat box for you, but don't unmute. It makes a lot of noise and makes disturbance to all other students. Okay. Now let us start our one. See, the first slide is going to be the introduction of what is called as the okay. Let us have some introduction regarding what is alkyl halide. Yes, you got this slide, all of you. Got it? Okay, sir. Okay. Let us discuss about this one. Let us see. This is first one is going to be the what are the alkyl halides. Okay, this is all already you know, but just look at on this one. Do you know haloalkanes and haloarenes persist in the environment? Haloarenes were used as herbicides during Vietnam War for defoliating the jungles and making it easier to fight in the war. These haloarenes cannot be decomposed and broken down by microorganisms like bacteria, as a result of which it is still intact in the soils of the jungles to this day. Okay, these are all not much important, but you go through this one and later I will share this video because we are now in a hurry to know the compute for the CPGET examination. See, let us have an IUPAC nomenclature. See, in the naming of a compound, you have to follow certain set of rules called as nomenclature. In this, let us have what is this IUPAC format. Find the parent chain as the longest hydrocarbon. This you know. Find the functional group, what it will be. It is going to be the suffix. Find the substituents and its position. It will be the prefix. And the functional group will be from suffix or prefix depending upon the priority series. This is going to be the different priority series, and that you know. But our main motto is to alkyl halides. Yes, what?
కానీ కొంచెం ఆగి నేను ఫోన్ చేస్తారా అదే కట్ చేస్తున్నా
See, and this is the common name nomenclature of alkyl halides. Let us see this one. The IUPAC name of haloalkanes is important for us. For this numerical position, alphabetically placed halo, root word, and ane. That is, you have to position of the this is the halo is a prefix, and you have to put a root word, and then if it is a alkane, you have to write ane. For example, here N-propyl chloride. This is a common name, but 1-chloropropane is IUPAC name. This is the isopropyl chloride and 2-chloropropane. This is N-butyl chloride and 1-chlorobutane, isobutyl chloride and 2-chlorobutane. Okay, this is going to be the tertiary butyl chloride and 2-chloro-2-methylpropane. Here, this nomenclature is not much important for entrance examination, but you have an idea regarding this also for that reason. And here, this is going to be the aryl halides in the case of the aryl halides. And in this nomenclature system, the naming of numerical prefixes depends on the basis of the position of the halogen atom in the aromatic ring. This is not one. Okay, here you know this is 1,2 position, 1,3 position, 1,4. 1,2 is called ortho, 1,3 is called meta, 1,4 is called as the para. See, this is going to be the 1-iodo-2-methyl-benzene. This is 1-iodo-2-methyl-benzene. And here, what is the name here? 1-chloro. This is going to be the chloro. And 4, because here 1, 2, 3 at 4th position, you keep a bracket. And what is this group? 1, 1, 2, 3 here. 2-methyl-propyl benzene. Here 1, 2, 3. There are 3 carbons are there. Its second carbon is a methyl group. That's why it is called 2-methyl propyl benzene. Now, the dihaloalkanes having identical halogen atoms are termed as alkylidenes or alkyline dihalides. They can be divided into 2 types. Geminal dihalides, when the halogen atoms are placed on the same carbon atom. Vicinal dihalides, when the halogen atoms are placed on the adjacent. You remember these 2 terms are important. Gem and Vic. Geminal dihalides means when 2 halogen atoms on the same carbon. Vicinal halides means or weak dihalides means on the adjacent carbons. See, for example, here this is going to be the geminal dihalide because the 2 halogens are present on the same carbon, whereas here 2 halogens are present at 1,2 position, 1,2 dichloroethane. This is 1,1 dichloroethane. This is 1,2 dichloroethane. Here, when halogens are present on the adjacent carbon, you call it as 1,2 dichloroethane. Now let us see what is the classification of the haloalkanes. Here, this is based on the hybridization of the carbon. Here on sp3 hybridized carbon and sp2 hybridized carbon. When it is sp3 hybridized carbon, we call it as the primary, secondary, tertiary, allyl halide and benzyl halide. See, primary alkyl halides, you know that is 1 carbon. 1 carbon means when carbon attached to only 1 carbon atom. If the halogen attached to the primary carbon atom, those are called as the primary alkyl halides. If you go for the secondary alkyl halides, that is going to be the carbon atom is simultaneously. See, the carbon atom is here. The carbon atom is here. It is simultaneously linked with the 2 carbon atoms. It is simultaneously linked with the 2 carbon atoms. That's why it is called as the secondary carbon atom. And when halogen attached to the secondary carbon atom, it is called secondary. Here, when carbon attached to the 3 carbon atoms simultaneously, that is called as the, we call it as the tertiary carbon atom. Here carbon, here also carbon. When it is attached to 3 carbon atoms, in that cases, we call it as a tertiary carbon. When halogen is attached to this tertiary carbon, those are called as tertiary alkyl halides. And here allylic halides. Allylic means you remember here, this is going to be the vinyl. And here when one more carbon is adjacent to this vinyl or alkene, and this is a 3 carbon atom, but halogen is attached to the sp3 carbon atom. That is why it is called allyl carbon atom. And here this is allyl carbon, and the halogen attached when attached to the allyl carbon, that is called allylic carbon. What is benzylic carbon? You remember here, it is not, halogen is not directly attached to the benzene. It is attached via a carbon atom. CH2 group. That's why whenever it is that is C6H2, benzene contains a CH2 group and X. In such cases, we call it as the benzylic carbon. And here you see this is the vinyl. See the difference between these 2. What is the difference between these 2? Vinyl halides and allyl halides. What is the difference between these 2? The difference is between these 2 is here this is the vinyl, and for this one more carbon when it is attached, that is going to be the CH2X. When it is attached like this, then it is going to be the what is called as the vinyl halide. And here this is aryl halide. See the difference between these 2. And what is aryl halide? What is benzyl halide? Aryl halide means halogen attached to the directly to the benzene ring, whereas here the halogen is attached via a CH2 group. In this way, the halogens are classified based on the hybridization. Now let us say they can be classified basis of number of hydrogen atoms. Compounds with sp3CX bond and another one compound having sp2CX bond, and here number of hydrogen atoms. On the basis of the number of hydrogen atoms, they can be divided into mono, di, poly, that is tri, tetra, and so on. Compounds having haloalkanes or haloarenes. It is named depending on the number of halogen atom these compounds contain in their structure. Let us take some example. This is called monohaloalkane because only one halogen. This is called dihaloalkane. This is the 2 halogens are present on the adjacent carbon atoms, and that is called wick. మనం తెలుగులో చెప్పాలంటే విక్ అంటే పక్క పక్కన అని గుర్తుపెట్టుకోవాలి. ఇక మనం కన్ఫ్యూజ్ కాకుండా విక్ అంటే ప్రక్కన ఉంటే విక్ dihalides. When the 2 halogen atoms are on the adjacent side, we call it as the wick dihalides. This is the dihaloalkane. Another is said to be the trihaloalkane. 3 halogens are present. Now let us go for the another example. Here, monohaloarine, this is dihaloarine, ortho position. This is trihaloarine, ortho and meta positions. Okay, some even important kadu. These are not much important, but you should have a simple idea. Endukante chala rojulu this is in the first year topic. That's why you have forgotten, I think. Sorry. Monohalo compounds can again be classified into the on the basis of hybridization, the carbon atom with the halogen attached. See, already we discussed this one. Compounds with sp3-CX bond, here X is halogen, fluorine, chlorine, bromine. These compounds can be further divided into the three types. They are alkyl halides, haloalkanes. In the class, halogen atom is attached to an alkyl group. The general homologous formula for this compound is CnH2n plus 1 plus X. Here, actually, we know that see, when you say CnH2n plus 2, that is alkane. One hydrogen is replaced by halogen. That's why we call this one. Now, they are further classified into mainly three types on the basis of the carbon atom to which the carbon-bearing halogen atom is bonded, primary, secondary, and tertiary. This classification is based on the nature of the carbon atom. This already I told you. Here, this is a primary because this carbon atom is attached to only one alkyl group. Here, this carbon attached to two alkyl group. This carbon attached to three alkyl group. This is already just now I told you. See, you have to know what is allyl halide. The carbon-carbon double bond structure is also known as allylic carbon. Thus, name is allylic halide. See, this is going to be the allylic halide. And here, this is going to be the carbon-carbon double bond, and here it is CH2. When such a group is there, this is called as allylic halide. Now, what is vinylic halide? This is also called vinylic halide. See, this is CH2, here is CH2 Here, this you remember, this is also vinyl, this is allyl. This is going to be the vinyl, this is going to be the allyl. Why I am saying this allyl? CH2, CH2, and here one CH. That's why this is with respect to the allyl, this is with respect to the vinyl halides. Now, let us see what are the benzyl halides. The sp3 hybridized carbon atom should be present next to the aromatic ring, like this. Whenever we have a compound like this, that is, this is a benzene ring, aromatic ring, here is CH2. And next to here, this is in this called as the benzylic halides. These terms ఎప్పుడు మనలో కన్ఫ్యూజ్ చేస్తూ ఉంటాయి. Benzylic, aryl, allyl, vinyl. These compounds every time we are getting confused. That's why try to remember what are these terminology. And see, compounds having sp2c bond. This is the case here. This is going to be the vinyl, and here also vinyl. This is called vinyl. In the మనం చెప్పుకున్నప్పుడు అది allyl. When the double bond is present here, that is going to be the vinyl. When the double bond is here, this is going to be the vinyl. When double bond is here, that is allyl. And you remember, this is going to be the vinyl group and vinyl halide. This is also an example for the vinyl halides. And aryl halides, when the directly attached here, when benzene ring directly attached to halogen, in such cases we call it as the what is called as the aryl. Okay, what I want to tell you, you must remember what is vinyl halides. What is vinyl halides? What is allyl halides? Because most of the time we are getting confusing with this only allyl, and another one we can say benzyl. Another we can say that is going to be the benzyl. At least you remember this terminology. What are these compounds? It is familiar to. Another one I want to tell you what is gem dihalides and what is weak dihalides. This is. And this term also you remember, because these are getting confused most of the students. What are these one? You remember, try to remember this term. See, let us having some, write the structures of the following organic halogen compounds. Perfluorobenzene we want to write. How to write the perfluorobenzene? See, this is going to be the structure. Perfluorobenzene, nothing but there is no hydrogen in the benzene. Instead of the C6, its formula is C6F4F6. That's going to be the perfluorobenzene. See, can you name this compound what it is? This is going to be CH2Br, CHCl, CHCl, CH3. Then how to name this one? Here 1 carbon, 2 carbon, 3 carbon, and 4. This is going to be the 1 bromo, 2, 3 dichlorobutane is its name. 1 bromo, 2, 3 dichlorobutane. Now, you know, this is iodopropane. That is, these are very simple. This is going to be the fluorocyclopentane. That is going to be here. This is going to be the, can anybody name this compound? Can anybody name this compound? Can anybody name this compound? I'm looking for your response. Can anybody name this compound? Chat. You post your answer in the chat box. 2-iodo-2-methyl propane. Very good. Very good. Okay, this is going to the 2-iodo-2-methyl propane. Okay, right. Very good. Now let us go for the another one. See, 2-iodo-2-methyl propane is the name. Can anybody name this compound? Bromopentane. 2,5-dibromopentane. Okay, right. 1, 2, 3, 4, 5. 2,5-dibromopentane. You are right. Very good. 2,5-dibromopentane. This is going to be the 2,5-dibromopentane. 2,4-dibromopentane, not 2,5. Okay, can anybody name this compound? It is not 2,5, it is 2,4. You mistaken. 2,4-dibromopentane is right. Rakesh, right. Anusha, you make it change it as 2,4. Can anybody name this compound? Can anybody name this compound? No? Nobody trying. 4-chlorotoluene, right. 1, 2, 3, 4. 4-chloro. No, not how it is 3-chloro. Here, this is the first carbon, second carbon, third, and this is 4. Sneha, it is 4-chlorotoluene. Okay, Swati is right. Redmi 1-methyl 4-chlorobenzene. Actually, here generally we call it as a toluene compound, but there is some ambiguity. Actually, we can say methyl benzene. Okay, 1-methyl 4-chlorobenzene. Let us see what will be the answer for this one. See, 4-chlorotoluene is the right answer. Now, okay, this is not ended. We'll go for, I will share another slide. Okay, now I want to share another slide that is going to be the second one. Okay. I hope you received slide. Slide వచ్చింది కదా మీకు. Can anybody respond? Are you seeing the slide or not? I want to know. Okay. What is there on the slide? Can anybody type? What is there so that I know that you are looking the right slide? Can anybody write what is you are looking on the slide heading? మీరు ఏం చూస్తున్నారా? Okay, right. Chemical reactivity. Okay, right. See, that other one is going to be the chemical reactivity of halogen compounds. What are the chemical reactivity of halogen compounds? Now let us see. This is the important from ఇందాక టాపిక్ ఏంటంటే జస్ట్ మీకు halogen compounds ఒకసారి ఇంట్రడ్యూస్ చేద్దామని, because you have learned in the first year itself. That is that topic is there, and here, and we will going to discuss now. From here onwards, it is very important for your examination. We will going to discuss two topics in this one. One is the chemical reactivity of halogen compound. Another is the formation of the Grignard. Now let us see the first one is sorry. Let us see the first one is the chemical reactivity of halogen compounds. See, alkyl undergo mainly two types of reaction. What are those? One is nucleophilic substitution reaction. Another is the elimination. These are two types of very important reactions that undergone by the alkyl halides. Now let us see, this is, you know, that alkyl halide. This is, let us discuss about how does a nucleophilic substitution reaction. The alkyl halide bond in halogen compound is polar in nature because of the higher electronegativity of the halogen over carbon atom. This can be represented as X. This is going to be this X. The carbon of CX bond is partially positively charged and hence shows acidic property of electron deficient atom or electrophilic character. So it is readily attacked by nucleophile. Halogen compounds readily undergo nucleophilic displacement reaction. I think you understood what is actually happened. Here, this is a carbon belongs to the fourth group element and this is going to be the seventh group element. Definitely this is more electronegative, therefore it gets partial negative charge. This will get the partial positive charge. This is you will get the partial positive charges here. And that's why it is highly polar bond. So that see what is happens when alkyl halide is attacked with a nucleophile. What happens? This nucleophile will attack the carbon atom and this halogen will be substituted. This is what is called nucleophilic substitution reaction. The reaction which involves one nucleophile is substituted over the other nucleophile is called as nucleophilic substitution reaction. Then what is elimination reaction? The elimination is mainly beta hydrogen. That is, see here, actually, what is this? How does an elimination occur is here. See, when this is treated with mainly, you remember, generally alkyl halides undergo elimination reaction when it is treated with the alcoholic KOH. When it is treated with the alcoholic KOH, how does it happen? See, this halogen of one carbon and hydrogen of on the adjacent carbon. This is called beta elimination because the hydrogen is eliminated from beta carbon, not from here. Don't get confused. Never hydrogen and halogen on the same carbon is eliminated. Only when alpha hydrogen, that is from this carbon to this one, the beta position, when this hydrogen is available, then only they undergo elimination. That's why it is called as the, what we call it as the beta elimination. See, in this way, the elimination will occur. This is beta hydrogen is present. They are acidic in nature. So in the presence of strong base and under suitable conditions, they may undergo elimination reaction. Example, dehydrobromination of ethyl bromide in the presence of alcoholic, what is called as the KOH. See here what is happening. You remember, for elimination of alkyl halide, only alcoholic KOH is better and suitable. See, bromine is replaced here when the hydroxide ion or OH minus ion taking this hydrogen. This will take the hydrogen and it is removed in the form of water. It is removed in the form of water like this. And here this elimination takes place and in the same time Br will be takes place. In this way, the elimination will happens, or this is called as beta elimination. Now other one, how does the reduction occur? Alkyl halides when reduced with the nascent hydrogen produces alkane. There are 5 reducing agents. You remember this reducing agent. You remember these are a very important reducing agent. Hydrogen over metal catalyst means that is nothing but nickel, platinum, palladium. Zinc and hydrochloric acid, hydrogen and phosphorus. This is red phosphorus. Lithium aluminum iodide or magnesium with H2O. Okay, here they produce as the nascent hydrogen. These are all reagents will produce as the nascent hydrogens. And you know that nascent hydrogen is always kept in a square bracket, which is called as nascent hydrogen and highly reactive. See, the alkyl halide, whenever you treat it with any of this reagent, this simply takes the hydrogen and here this X is converted to HX and alkyl group is converted to alkene. Remember that alkyl halides can be converted into the alkane by any one of these reagents. Say, for example, if you take the ethyl bromide when treated with the red phosphorus and hydrogen iodide, you will get the methane. And another some other reducing agents also used. Zinc copper couple, sodium in ethyl alcohol may also used as reducing reagents. You remember here this is 1, 2, 3, 4, 5, and this is 6, and this is going to be the 7. Among these 7 reagent, any one of the reagent then carry this transformation. Alkyl halide to the alkane. Now let us see other one. Alkanes can be prepared by the reduction of alkyl halides with the help of the different methods. Reduction by dissolving metals, an alkane is produced when zinc reacts with the alkyl group. See, let us take an example. See, that is zinc in presence of any halogen acid. When treated, this produces what is called as the nascent hydrogen, and that will be converted into the alkane. Now let us say some other reactions. See, this is alkyl chloride, and when it is treated with the zinc and hydrochloric acid, you'll get zinc chloride and alkane is resulted. See other reaction, transforming of electron from metal to the substrate, followed by the transfer of proton from the acid. See, actually how this mechanism takes place. First, this is, this zinc is highly electropositive metal. During the course of reaction, it releases 2 electrons. And these electrons are taken by here. See, these electrons are taken by this alkyl group, which is formed here, and it is going to be the negatively charged. And this now take the H plus ions from the acid, and so that it converts into the alkane. And this chloride ion now reacts with this zinc plus ions, which is formed in the reaction. Finally, you will get a zinc chloride. That is, this is going to be the electron transfer occurs from zinc metal to the alkyl group, followed by the extraction of the proton from the HCl that is used in this reaction. Now let us see other one, reduction by lithium aluminum hydride. Reduction by lithium aluminum hydride readily reduces primary and secondary alkyl halides to alkane, while tertiary alkyl halides gives alkenes. You remember, this is a very, very important point. The tertiary alkyl halides will give the compound is called alkenes. Now let us take this one, alkyl halide with lithium aluminum hydride. This also produces nascent hydrogen, and that will give the alkane. See, this is the case. Some examples, hydride transfer occurs as follow. This is going to be the lithium aluminum hydride, and that will give the, see here, 1 hydrogen is given to this alkyl halide, that's why it is alkane. And there is another hydrogen also transferred to the alkyl halide, you will get 1. This X is taken by alkyl lithium aluminum hydride, that will be converted like this. See, there are 2 more hydrogens are there, that's why it will reduce 1 more alkyl halide. And here finally what you have to remember, 1 lithium aluminum hydride molecule can produces 3 molecules of what is called as alkyl. 4 molecules of alkyl halide converts into the alkane. This point you have to remember. And now another one is the reduction. Tertiary alkyl halides are reduced by sodium borohydrides to the primary alkyl. This is what is called as hydrogenolysis. Alkanes can be replaced by the hydrogenolysis of alkyl halides in the presence of palladium charcoal used as a catalyst. Okay, sodium borohydride also we can use, and another one is the palladium charcoal also, that also produces alkane, and that is a catalytic hydrogenation. This is what is called as. Now let us see the other one. Till now we discussed about the reactivity of the halogen compounds, mainly focused on the reduction. Now let us see formation of the Grignard reagent. You know, this is a very, very important compound in the organic chemistry, because this compound, because of this, from this compound, you can prepare any compound in the organic chemistry. Grignard reagent has a formula RMGX, where X is a halogen and R is an alkyl or aryl based benzene ring group. For the purpose of this we shall take R to be an alkyl group. A typical Grignard reagent is ethyl magnesium bromide. Now let us see, this is other one is going to be the how a Grignard reagent can be formed. The preparation of Grignard reagent. Grignard reagents are made by adding the halogenoalkane to the smaller bits of magnesium in a flask containing ethoxyethane, that is called ether. commonly called diethyl ether or ether. This flask is fitted with a reflex condenser and the mixture is warmed over water bath for 20 to 30 minutes. You remember one important point regarding the Grignard reagent. For the preparation of the Grignard reagent, there must be ether. That means there must not be any moisture in the reaction. And in this case, when ether is present, then only this reaction occurs. Suppose instead of the ether, water is there. In such cases, what happens? The magnesium react with the water and liberate hydrogen because it is highly reactive. Therefore, the Grignard reagent does not form. That's why the condition must be ether solvent. See, everything must be perfectly dry because the Grignard reagent reacts with the water. Now let us see this one. The carbon atom of organic halide, which is directly attached to the halogen, is of course electrophilic. This electrophilic reactivity can be switched to nucleophilic reactivity of the conversion to organo-magnesium halide, that is called Grignard reagent. This is going to be the alkyl halide. You know, this is going to be the partial positive charge. This is partial negative charge because it is a polar covalent bond. When magnesium is treated with, what happens? The magnesium, because it is highly electropositive, then it adds on the middle of the alkyl and halogen group. Therefore, its valence is satisfied because this is going to be the dipositive charge. This is minus now. This is going to be the minus. Okay. Remember, before going to formation of the alkyl magnesium halide, that is Grignard reagent, alkyl group or carbon atom has positive charge. After the formation, it's going to be make a negative charge. Especially note that the carbon magnesium bond in Grignard reagent is polar covalent with carbon being negative end of the dipole. That you have to remember. Thus, the nucleophilicity of carbon in a Grignard reagent. Note also that the magnesium halogen bond is largely ionic as shown in the structure above. That is a very, very highly polar bond. The mechanism of the formation of a Grignard reagent is shown below. Like the other reaction considered in this, it is also involves a radical intermediate. There is one major difference. However, Grignard formation does not involve a radical chain mechanism. It is a non-chain radical reaction. See, this is going to be the how a Grignard reagent is formed. This is alkyl halide. First, the electrons are transferred to the what is called as it is transferred to the halogen. And here, what happened? The bonded electron, one of the electron goes to here, one electron goes to here, so that we get alkyl radical and X minus. How does X minus is formed? Because it was taken one electron from the magnesium and other electron from the covalent bond. That's why it is going to be X minus, because it is loss of one electron, therefore a unipositive magnesium. This is an intermediate, it is not possible to isolate. Then after that, again this electron and this electron of the alkyl group then involved in the polar formation of the polar covalent bond. In this way, the Grignard reagent is formed. The first step is the rate determining step. Now let us see formation of, note that the first step is a rate determining step and involves the transfer of one electron from magnesium, which has two electrons in its valence shell, to the carbon halogen bond. This forms Mg+1, which is a radical. This is then couples with the alkyl radical form. Just now I told you that. Now see this one. This is going to be diethyl ether is an especially good solvent for the formation of the Grignard reagent, because ethers are non-acidic, that is aprotic solvents. Water or alcohol would protonate and thus destroy the Grignard reagent, because the Grignard reagent carbon is highly nucleophilic. You remember that water should not be present in the Grignard reagent, as it reacts with the Grignard reagent and form alkane and disturb the Grignard reagent. That's why you should use a polar, that is non-acidic or aprotic solvent like ether only. This would form a hydrocarbon, but Grignard reagents are stable in ether only. Okay. Now let us see other one. This is going to be a Grignard reagent. Suppose if any water is present, a small moisture is present, then Grignard reagent react with this one and converts into the alkane. That's why the Grignard reagent will be disturbed. Of course, sometimes we need to prepare the alkanes from the Grignard reagent so that when it is treated with this one, you will get this alkane. Another reason that ethers are good solvent for Grignard reagent is that the MgX bond is ionic and thus benefits the greatly forming being effectively solvated. The formation of ion in very non-polar solvent where they would not be effectively solvated is very difficult. See, ethers are surprisingly good at solvating cations because the carbon-oxygen bond is relatively polar, thus allowing the oxygen end of the ether dipole to solvate and stabilize the magnesium ion. You can see here how does it is solvated. Here, this is going to be the diethyl ether. This is going to be the diethyl ether. Here, oxygen has negative pole and ethyl group has positive pole. And this negative pole of the ether will be solvated with the positive pole of the magnesium. That's why this Grignard reagent is solvated, and that's why ether is a good solvent for the Grignard reagent. See, let us see this one. Ethers are, this already I told you this one. Now let us see this. For a given alkyl group, this is very important for your competitive examination, very, very important. The ease of formation of the Grignard reagent is in this order. Okay. For suppose when it is all these are allowed to react with the magnesium, you remember this is going to be the order of reactivity. Alkyl halides are more reactive than bromides. This is more reactive than chlorides. See here, for example, methyl iodide, ethyl. Okay, this is with respect to the halogen. With respect to the alkyl groups, now with the same iodine, but with respect to the halogens, with increasing the bulkiness of the alkyl group, the ease of formation of the Grignard reagent will be decreases. This point you have to remember. That means one point is iodides are more reactive than bromides, bromides are more reactive than chlorides. And in the case of the alkyl groups, are a halogen, this one. And in this case, methyl is more reactive than ethyl, ethyl is more reactive than propyl. Like that, with increasing the nature of the bulkiness of the alkyl group, the reactivity will be decreases. Nature of the Grignard reagent. Grignard reagents are having dual character as a base, as a nucleophile. What is that, the dual character? It acts as a base as well as a nucleophile. Let us take example. As a base, it is readily reacts with active hydrogen compounds to yield hydrocarbons. An active hydrogen compound is one which one will liberate hydrogen upon treatment with an active metal. See, this in this case it acts as a base. Suppose here Y is nothing but OH group or NH group. This is OCH and etc. In this case, what happens here? It takes the proton. It takes the proton. That is, alkyl group takes the proton, and we will get this is alkane. This is nothing but these are all protonated solvents. Actually, here something is missed. This is nothing but NH3. That is ammonia. This is nothing but what we call it as the here CHO. That is going to be the alcohols or any protic solvents. And in such cases, we'll get the alkane. Wherever in these cases, the Grignard reagent acts as a base. Now let us see how does it act as a nucleophile. This is very, very important. And in the organic chemistry, the reactions involving the Grignard reagent as a base is very, very less. But the reaction where the Grignard reagent is acting as a nucleophile is a greater and greater reactions. These are very important reactions. With this, when Grignard reagent is used as a nucleophile, a new carbon-carbon bond is developed. For making a new carbon-carbon bond, we use a Grignard reagent. See, for example, this is going to be the RMGX, alkyl magnesium halide. This is an aldehyde. In presence of acidic medium or a protic solvent, this will be converted into the what is called as the alcohol. See, one alkyl group is from the alkyl group, another alkyl group is from the aldehyde, so that you will get the alcohol. In this reaction, the Grignard reagent acts as a nucleophile. See, this is not at end, and we're going to take one more slide because I prepared. I've divided into the different parts. Let us go for the third one. This is the very, very important slide. Third slide is very important because we have the SN1 and SN2 reactions in these slides. I want to know that. I want to know this whether you are looking the slide or not. Is a slide is there? Are you the slide is visible to you or not? I want to know that. Please respond, anybody. Yes. What is there on the slide? Nucleophilic substitution. Okay, right. You are the slide is visible to you. Okay, okay. So let us see nucleophilic substitution reaction. These are very, very important. In this slide show and in this part, I am discussing one SN reaction and one more the next slide. What is nucleophilic substitution reaction first of all? Then let us see, there are two types of reaction. One is SN2 reaction, substitution, nucleophilic by molecular reaction. Another one is SN1 reaction, substitution, nucleophilic, unimolecular reaction. Now let us see, other one is nucleophilic substitution reaction. What is actually nucleophilic substitution reaction? Nucleophilic stands for nucleus loving, means nucleus attracting, means positively charged attracting. That means the species which attracts the nucleus or a positive charge are called nucleophiles. That means the nucleophiles having the negative charge or they are having electrons, that is excess electron or lone pair of electrons. And another one, in the same way, electrophiles, electron loving, that is electron seeking, they are electron deficient. Whereas here electron excess ఉంటుంది. Here electron density is more, whereas electrons are less. These are rich in electron, these are poor in electron. Electron deficient atom or group of atoms seeking electrons. Nucleophilicity, you remember this terminology. I am telling here what is nucleophile, what is electrophile, what is nucleophilicity. Nucleophilicity of a nucleophile depends upon its structure. Common nucleophile as listed here. See, the common nucleophiles are, 1 minute. See, nucleophilics, common nucleophiles are this one. These are the nucleophiles and they are related to reactivity. Very powerful nucleophiles are iodide. That is, this is thioalcohols basis one. This is alkyl sulfide. And good nucleophiles are bromide, hydroxide, alkoxide, cyanide, and azide. See, this is going to be their nucleophilic character. This is a very powerful nucleophilic character. Followed by these are in the range of 10 to 4. Here, the some digit is missed because some print mistake. And here, this is going to 10 to 4. Fair nucleophiles: ammonia, chloride, fluoride, and this is the carboxylate ion. Weak nucleophiles are water and alcohol. See, what is the reason here from here to here? These are the negatively charged. Negatively charged are powerful or good nucleophile. And fair, this is because there is a lone pair of electron, ammonia, and chloride, fluoride also be somewhat fair nucleophiles. But when you go for the water and alcohol, there are two lone pair of electrons. That's why these are said to be there. Of course, they also donate the electron pair, but when compared to these three categories, these are somewhat weak. Very, very weak nucleophile is carboxylic acid. See the difference here, carboxylate ion, here it is the carboxylic acid. Okay, and here this is taken as a unity, and the remaining all are compared with this water and alcohol. It is 10 to the power of 3 times greater. It is 10 to the power of 4 times greater. It is somewhat digit missed here. It is less than this water. This you remember. Sometimes you may get a question among the following, which will be a strong nucleophile, which will be weak nucleophile. In this way, you remember that. Okay. Among the halogen, iodide is strong, bromide is good, and chloride and fluoride are fair. Okay. This is the case. You remember. Now let us see nucleophilic substitution. A substitution reaction where a nucleophile replaces another nucleophile is known as nucleophilic substitution reaction. These substitution reactions are characteristic feature of alkyl halides. I told you that alkyl halides mainly undergo two types of reaction. One is nucleophilic substitution reaction, and there is elimination. Among these two are very important. And here elimination reaction, we already told you. This is going to be the nucleophile. The induced dipolar nature here, the carbon halogen is a polar covalent bond because the halogen is what is more electronegative, it is less electronegative because it is 7th A group element. This is going to be 4th A group element and creates partial positive charge and negative charge on the carbon and the halogen center. Here is the presence of a strong nucleophile, stronger than already attached to carbon. Incoming nucleophile replaces the halogen. That means here to replace this halogen, and here to replace this halogen, and the entering nucleophile must be a stronger than what? A stronger than this halogen. It must be stronger than halogen. In that case only it will be eliminated. That is, it will be leave. It is called as leaving group. This is called entering group. When another nucleophile, when a strong nucleophile approaches this alkyl halide, then only it will be substituted. Otherwise, halogen never substituted. Now see an example. This is going to be a nucleophile that is incoming, and this is going to be a leaving group. And here this alkyl group is replaced by this group, and finally you will get this new compound with the new nucleophile, and halogen is a leaving group. That means this is entering group and this is going to be the leaving group. It is a simple nucleophilic substitution reaction. And how does this undergo? Let us see. The first one is SN2 reaction. I told you that there are two types of reaction. One is SN2, another is the SN1 reaction. SN2 reactions. What is SN2 reaction? Nucleophilic substitution by molecular reaction. This substitution reaction is greatly influenced by nature of attacking nucleophile, substrate, and other one is leaving group. Means this SN2 reaction depends on the nature of attacking nucleophile, substrate, and leaving group. Substrate means here alkyl halide. That means it depends on the three factors. One is the entering, another is the alkyl halide, another is the leaving. In primary or secondary alkyl halides, attack of incoming nucleophile and displacement of leaving group takes place in a single group or in a single step. In the case of bulky tertiary alkyl halides, attack of incoming nucleophile and displacement of leaving group takes place in two steps. Hence, these substitution reactions follow two different mechanisms known as SN1 reaction and SN2 reactions. A simple example for SN2 reaction mechanism is reaction of methyl bromide with hydroxide ion base. The attack of incoming hydroxide ion at partially positively charged carbon atom carbon center displaces the bromide. I will tell you the mechanism. The formation of new bond of hydroxide ion and cleavage of the bromide bond of carbon center takes place in a single step. Let us see this mechanism now. Actually, the nucleophile pushes off the leaving group from the carbon. The kinetic data suggests that the rate of reaction is directly proportional to the concentration of both. This is a very, very important point. The rate of the reaction directly proportional to the concentration of both. One is said to be the alkyl, another is said to be the hydroxide. Thus, it is first order in each reactant and second order overall reaction. This is going to be the reaction. This hydroxide ion enters, and just now I told you a typical example before. And this go and adds here this carbon atom, and here it enters here, and this will be leave. And here you will get this a new compound, that is alcohol, and bromide ion is a leaving group. We will discuss the mechanism. How does this mechanism? The rate of the reaction is directly proportional to the methyl bromide as well as the concentration of hydroxide. That's why it is SN2. Substitution nucleophilic bimolecular reaction. That means the rate is a bimolecular reaction, means the rate determining step involves two molecules or two substances. One is alkyl halide, another is the base. And see, this is going to be the reaction. See, this is going to be the RDS. I think you know what is RDS, rate determining step. This is going to be the RDS step, and where it involves both of these two. And here, first of all, it attacks on this one. There is a new bond formed by this carbon between the oxygen OH and carbon, and this bond will going to be the weaken, and this is going to be the lengthen. Here, this is going to be the carbon bromine bond. Some bond length is there, that you know. When the OH is attacked on this carbon atom, what happens? The length of the bond will be increases, and this is a transition state. In this transition state, both are present. One is the hydroxide ion is present, another is the alkyl bromide is present. That's why it is going to be the SN2 reaction. And in this way, you will get alcohol and bromide is the leaving. Now let us see this. Therefore, it is a bimolecular reaction where both attacking nucleophile and substrate are involved in the formation of the transition state. In this transition state, carbon is bonded to both incoming nucleophile and departing leaving group. Such a reaction is known as bimolecular nucleophilic substitution reaction, denoted as SN2. Let us see this one. An interesting aspect of SN2 mechanism is 100% inversion of configuration at the reaction site. It means incoming nucleophiles carbon from the side opposite to the leaving group. This is a very important stereochemistry of SN2 reaction. In the end, incoming nucleophile get attached to the position opposite to the leaving group. See the action. See, this is a, let us take, okay, I have taken this is in a different way. Suppose if you take here a optically active compound, different groups, or here I I made a bond with the different planes, okay? And if it is an optically active compound, in that case also you can see. Here this hydroxide ion attacks on the opposite side, and the bromine is leaving group. In the transition state, here the bond making takes place, here bond breaking takes place. This bond in the weaken, and here the bromide ion is left. See, in the transition state, you can observe that the entering nucleophile always attacks on the back side of the carbon atom where the bromine is present. And these two groups are completely in opposite direction. Suppose in an optically active compound, suppose if you start with the dextro or then the product is always a levo compound. See, the product is either levo compound if you start with the dextro or S configuration, because the position of the entering group is quite opposite to the leaving group. This is a very, very important regarding the what is a SN2 reaction. Sometimes you may get a question in this SN2 reaction stereochemistry. Now let us see, this is in the transition state, the reaction center is surrounded by 5 groups and it is sp2 hybridized. See, the 3 hydrogen atoms are attached to it and lie in one plane with a bond angle with equal to 120 degrees. See, I want to tell you one more thing also here. This is the case. Here, this carbon now in the transition state, this carbon is sp2 hybridized and the bond angle is 120 degrees. These 3 are in the 3 different planes. This is above the plane, below the plane, on the plane. And the bond angle in the transition state is, sometimes you may get a question, what is the hybridization of the carbon in the transition state of SN2 reaction? That is sp2 hybridization. Now the nucleophile OH and leaving group are attached to the 2 loops of the unhybridized p orbitals of the reaction center. The carbon hydrogen bonds are thus arranged like the spokes of a wheel, while COH and C, that is halogen bond, or along with the bond tags. See, this is, I'll show this. The energy profile diagram SN2 shows the presence of single transition state at a highest energy state and no intermediate is found. The reaction is exothermic. The transition state is highly unstable due to presence of high energy and 5 bonds around the carbon atom. See, this is going to be what I want to tell you. Here, these 5 bonds like a spokes around in the wheel. మన సైకిల్ చక్రంలో మధ్యలో ఒకటి ఉంటుంది కదా, దాని చుట్టూ ఎట్లయితే స్పోక్స్ అరేంజ్ ఉంటాయో, and in the same way in the transition state the carbon is attached to the 5 bonds even though the carbon is only sp2 hybridized. These bonds are formed by the overlap of unhybridized pure p orbital. Only these bonds are with sp2 hybrid orbitals. And another one is, if you see the energy profile diagram, this is going to be the energy profile diagram. Here, this is going to be the reactants, that is before going to the reaction. When these are two are approaches, you will get a transition state. Here you will get a transition state, and the energy will be increases. Then again, after this bond is broken and this bond is forming, then activation energy decreases. Then you will get the products. See, the energy between the reactants and the products, this is going to be the lesser in energy, this is going to be the higher in energy. That's why we say it is a exothermic reaction. See, this is going to be the, finally the carbon bromine bond is fully cleaved. The energy required to it is partially provided by the COH bond formation. The OH group takes the position just opposite to the bromine atom. See, this is the case. In SN2, the nucleophile hits the carbon on the side opposite to the side bonded to the leaving group. The carbon is said to undergo backside attack. The orbital of the nucleophile overlaps with the smaller lobe of the sp3 hybrid orbital of the electrophilic carbon. This lobe is the side of the carbon directed away from the carbon halogen bond. Hence, the best overlap of the interacting orbitals possible through the backside attack only. The best way to visualize the movement of the groups bonded to the carbon at which substitution occurs is to picturize an umbrella that turns inside out. This is called as inversion of the configuration, or otherwise it is called as Walden inversion. That means in SN2 reaction, a Walden inversion takes place. See, this is the case happens. See, this is the unhybridized orbital. The hydroxide ion is attacked down here. This is the bromine. And so that in the, what is called, it is a transition state. It is a transition state where leaving group and that entering group both are present. And here, this is going to be the hydroxide and the backside. Inversion of the configuration takes place. This inversion is called Walden inversion. The Walden inversion is present in SN2 reaction. You can see this is the hence we can say when SN2 mechanism operating, the inversion must occur. This process often been linked to the turning inside out of the an umbrella. See, I will show you. And see, during the what I mean is cyclones, when you take the umbrella, what happens when this wind comes into this umbrella, then the umbrella will going to inside out. అది మొత్తం పూర్తిగా టర్న్ అయిపోతుంది అనమాట. టర్న్ అయిపోవడం వల్ల ఏమవుతుంది, ఇన్సైడ్ అవుట్ అవుతుంది. దిస్ ఈజ్ అవర్ జనరల్ ఎక్స్పీరియన్స్ ఇన్ ద డ్యూరింగ్ ది సీజన్. And here also there is an inside out, that is configuration is before the reaction is like this, after the reaction is inversion. This inversion is called as Walden inversion. Let us take some examples. Hydrolysis of 2-bromobutane. When R configuration of 2-bromobutane is hydrolyzed, we will get S2-butanol. See, this is the case. This is 2-bromobutane. This is the R configuration. See, the hydroxide ion attacks on the backside of the carbon. This is going to be a transition state, and you will get S-butanol. That means if you start with the reacting molecule with R configuration, you will get on the S configuration. See, another careful observation of the configuration R2-bromobutane and S2-butanol indicates that there is an inversion of the configuration of the product. Optical rotation plus minus or dextro and leave are nothing to do with the configuration. Just to simply remember, one is R, another is the S. This type of reactions are generally observed due to nucleophilic reagents or nucleophiles. In these reactions, A stronger nucleophile displaces a weaker nucleophile. The nucleophiles we already discussed. The rate of the reaction is directly proportional to nucleophilicity. The decrease in the nucleophility of some nucleophiles in the following order. That is methyl carbanion amide. It is stronger than the amide. Amides are stronger than the alkoxide. This is hydroxide, bromide, chloride, fluoride. See, because you remember we are discussing about the hydrolysis, means the hydroxide ion is a stronger nucleophile than bromide, than chloride, than fluoride. That's why whenever the alkyl halides are treated with the what is called as aqueous KOH, this reaction, when it is treated with the aqueous KOH, simply the halogen is replaced by OH. Okay, this is the case. Suppose if the OH you want to replace, then it is treated with the alkoxide. When you want to replace this alkoxide, you want to treat with the amide base. Then we want to replace this one, we will take this methyl anion. See, this is going to be the case. Now, see, the factors that affect the rate of SN2 reaction are structure of the substrate, the concentration and the reactivity of the nucleophile, the effect of the solvent, the nature of the leaving. All these influences the rate of reaction. You remember that sometimes you may get a question. The following factors influences the rate of the SN2 reaction. In such cases, you remember all factors: substrate, nucleophile, solvent, leaving. All are affect the SN2 reaction. Okay, you can have some good what I meant to say animation on this link. This is not ours link. This is other link, and it is a good explanation how does it happens. Later you can watch that one. It is not yet completed. One more slide is there. I want to share. That is SN1 reaction I want to explain you. And this is going to be the SN1 reaction. See, let me open this slide. This is going to be the, now we're going to discuss what is SN1 reaction and what are the differences between the SN1 and SN2. We'll discuss here. We are discussing about, we discussed about SN2. Now let us take SN1 reaction. Substitution nucleophilic unimolecular reaction. Let us see what is this. Tertiary butyl bromide does not undergo substitution via SN2 reaction. ఇందాక మనం ఏం చెప్పుకున్నాము, what we discussed, only either primary alkyl halides undergo what is called as SN2 reaction. Primary alkyl halides undergo SN2 reaction, and now we are discussing tertiary alkyl halides undergo SN1 reaction. It undergo SN1 reaction. Now tertiary butyl bromide does not undergo substitution via SN2 reaction. Then what happens actually? These bulky halides actually undergo nucleophilic substitution reaction following slight different mechanism, that is called as SN1. This is going to be the tertiary butyl bromide. During the hydrolysis, it will give tertiary butyl alcohol. This is not undergone by SN1 reaction. This undergo by SN1 reaction. Let us see what is this. The kinetic data shows that the rate of the reaction depends only on the tertiary butyl bromide. Does not depends on the concentration of the, that is nucleophile. Only depends on this. The nucleophile water in the above equation does not contribute to the rate of reaction. Adding even a stronger nucleophile does not influence the rate of reaction. The reaction thus follows the first order kinetics, where rate of reaction is independent of concentration and nature of the nucleophile. Moreover, nucleophile does not participate in the rate determining step. This reaction mechanism is called unimolecular substitution reaction, or in another way, SN1 reaction. See, let us see the rate equation. The rate of a reaction is equal to K into tertiary. That means the rate depends only on the concentration of the alkyl halide, but not concentration of the nucleophile or water. See, this is the case. The step 1 is a slow step, and the slow step always we call it as the RDS. What is RDS? RDS means rate determining step. And this is a slow step. In this slow step or rate determining step, only alkyl halide is present. And here in this slow step, the ionization takes place, the formation of the carbocation, and the bromide ion is formed. And this is the important for us now. In the first step, alkyl halide dissociate to form carbocation and halide ion. This is a slow step, and hence it is called as rate determining step. The formation of carbocation is fundamental feature of SN1 mechanism. You remember, in the case of SN2, there is no formation of carbocation, whereas here the formation of the carbocation. Now let us see, this is going to be in the step 2. This carbocation, tertiary carbocation, now attacks this nucleophile, that is water molecule. You will get an intermediate which is called as this oxonium. In the case of the SN2 reaction, we didn't get any intermediate, direct transition state to direct to products. But here you'll get an intermediate that is called tertiary butyl oxonium ion. Now let us see this one. In step 3, it is going to be the proton is extracted by or attracted by this water taken by this water, and it converts into the hydronium ion, and you'll get the tertiary butyl. That means in the case of SN1 reaction, it involves 3 steps, whereas in SN2 reaction, only 1 step: nucleophile attack, transition state, directly product. But here, formation of carbocation, then attacking of nucleophile, and the third step is the loss of the proton. Here it involves the 3 steps. In the last step is fast acid-base reaction. Here water acts the base and remove the proton from oxonium ion to give final product, tertiary butyl alcohol. Now see, this is going to be the energy profile diagram of SN1 reaction. See, this is a tertiary butyl bromide. Here, you see here, there are 2 transition states, transition state 1 and transition state 2. In transition state 1 is in the first step, where that is a carbon bromide bond is going to be weakened, and here when it is approaches, the bond going to be weakened, and the energy of the alkyl halide increases, and then after losing, okay, I will tell you here, then what happens after getting a higher energy state or transition state, the bromide ion is lost. Again, it forms what happens? A tertiary carbocation is formed like this. After this formation, what happens? After the leaving this, after formation of the carbocation, again the energy decreases. And after decreasing, this is the first step. And in the second step, this is going to be the formed carbocation. And here the hydroxide ion will going to be the hydroxide ion is going to be the, what happens? It is going to be approaches this carbocation. Then again the energy increases, then you will get the second transition state. You remember, in SN2 reaction, only 1 transition state is possible. In SN1 reaction, and 2 transition states are possible. See, this is going to be the stereochemistry. The 2 products formed when a chiral substrates are possess an asymmetric electrophilic carbon is applied in SN2 reaction. One of them has the same object. That means in the case of the SN2 reaction, only inversion of the configuration takes place. Only 1 product is possible in the case of the SN2 reaction. But here in SN1 reaction, 2 products are possible. One is the what is called as the same according to the reactant molecule. Another is opposite. The 2. One is a retention, another is the inversion configuration. Let us discuss this. In contrast, the other product possesses the opposite and absolute configuration called inversion. One is a retention, another is the inversion. In SN2 reaction, the nucleophiles exist the substrate before the nucleophilic attack can ever occur. Thus, an intermediate carbocation is then formed. Due to the carbocation is trigonal planar shape, its 2 anisotropic sites are susceptible to attack by the nucleophile with the same probability. This, you can see this reaction. See, this is going to be the carbocation intermediate. This is formed from alkyl halide 1, 2, 3. These are the, according to the CIP rules, their priorities. I'm telling here. This is the 1, this is 2, this is 3. Now here carbo, that is the when bromide ion is lost, you will get the carbocation. It is a trigonal planar shape, and this trigonal planar has attacking of the entering nucleophile, attacking the nucleophile, have chances to attack on both sides, either on the same side, that is bromine is present, or on opposite side where the position to the opposite to the bromine, that is leaving. So that when it is on the same, you will get this is going to be the alcohol. This is called as the retention of the configuration, where the nucleophile take the same position as the leaving group. Whereas when the nucleophile attacks opposite to the leaving group, then you will get this is going to be the one, and this is the alcohol. This is called as inversion of the configuration. Therefore, there are two possibilities and equal possibilities, equal chances. That's why you will get 50% retention and 50% inversion. That's why in the case of SN1 reaction, the racemization takes place. Here, the racemization takes place here. Whereas in the case of SN2, only inversion of the configuration takes place. Here, racemization takes place. A racemic mixture is found because the front side attack and back side attacks leading to two opposite configuration products. That means two enantiomers. SN1 reaction of 2-bromobutane, either R or S, is a racemic process because the nucleophilic attack from either side is equal, sorry, which results in equal amounts of two opposite configuration, that is R and S 2-butanol. See, this is going to be the formation of an object and its mirror image product in equal proportion called racemization. So SN1 reaction involves racemization process, whereas SN2 reaction involves formation of inversion of the configuration. Okay, this is another URL where SN1 reaction is explained with an animation. You can go and click on that URL, then you'll get what is called as a beautiful animation here. See, let us see, this is a very important factor you have to know. What are the differences and comparative between the SN2 and SN1? Sorry. Then let us see. Characteristics of SN2 reactions. It is a single step reaction. Rate of reaction is directly proportional to the both alkyl halide and nucleophile. It is a second order reaction. Rate is dependent on concentration and strength of the nucleophile. Transition state is formed, which is sp2 hybridized planar structure. And here not sp3d, you remember, because transition state contains 5 bonds, but don't say that it is going to be sp3d hybridized. It is only sp2 hybridized because the 2 bonds, that is where the entering and leaving group are present, they are that this is only pure orbital only involved, no hybridized orbitals. That's why this is not sp3d hybridized, even though the transition state is having 5 bonds. No carbocation intermediate formed. Here no carbocation intermediate. Then let us, leaving group should be strong, that is a weak base. Rate of the reaction is inversely proportional to the bulkiness of the group attached to the carbon atom. That is, it is methyl chloride, ethyl chloride, this is isopropyl chloride, this is going to be the tertiary butyl chloride. That means in the case of SN2 reaction, that is another way, primary alkyl rate of reactivity, primary alkyl halides is greater than the secondary, this is greater than the tertiary, like that. Rate of reaction 1 degree greater than 2 degree greater than 3 degree. Strong nucleophile performs SN2 reactions. Nucleophile attacks substrate directly from the backside. Polar aprotic solvents like DMSO, DMF, DMA favors SN2 reactions. That is dimethyl sulfoxide, dimethyl formamide, dimethyl ammonia favors SN2 reaction. Because PAS means polar a protic solvent does not dissolve or solvent cations, and it dissolves only anions in solution. So by taking PAs, cations are removed and only nucleophile is only anion present to attack the substrate. Walden inversion occurs in SN2 reaction. Reactions is favored by low temperature and high temperature. Sorry, low temperature. Suppose if the temperature is increased, what happens? The elimination takes place. That elimination is called E2 elimination reaction. Now let us now take what are the characteristics of SN1 reaction. It is a two-step reaction. Rate of a reaction is directly proportional to the only alkyl halide. It is a first order reaction. Carbocation intermediate is formed. Rearrangement of carbocation is also possible. Rate depends on the stability of the carbocation. That's why tertiary carbocation is more stable than the secondary. Secondary is more stable than the primary. Rate of reaction is also depends on the stability of cation and anion. Polar protic solvents, the favors SN1 reaction. These are called PPS solvent, polar protic solvent. Dissolves both cation and anions in it. Leaving group should be strong. That means a weak base, same as in SN2. This point is same for the SN1 and SN2. Weak nucleophile performs SN1 reaction. Strong nucleophile will directly attack substrate, resulting even elimination. Therefore, we need only weak nucleophile. If it is a strong nucleophile, that leads to the elimination, that is even elimination takes place. Rate of reaction is independent of concentration and strength of the nucleophile. Products formed will be both R and S form, that is mirror images, or we can say that is two stereoisomers are formed. Low temperature, this is also same for both. Low temperature favors SN1 as well as SN2. If the temperature increases, elimination takes place. Okay, now let us see, this is going to be some differences between the SN1 and SN2. Rate law, unimolecular, bimolecular, big barrier, carbocation stability, it is going to be the steric hindrance. Alkyl halides 3 degree followed by 2 degree and 1 degree never follow in SN1 reaction, and whereas SN2 1 degree is more and tertiary never follow SN2 reaction. And depending on the condition, the secondary alkyl halide may undergo SN1 as well as SN2 depending on the solvents used. See, that is I told you that this is polar solvents. Suppose the same reaction is carried as secondary alkyl halide in polar solvents, you'll go for SN1 reaction. If it is a non-polar solvents, this goes in SN2. That is, only the secondary alkyl halide can involve in SN1 reaction as well as in SN2 reaction. This is only. But you remember, primary is always SN2 reaction, tertiary is always SN1 reaction. And here stereochemistry, here mixture of retention and inversion means racemization takes place, whereas here Walden inversion only takes place. The mechanism for SN2 is concerted. The mechanism of SN1 is stepwise, means SN2 reaction involves only single step, whereas SN1 reaction involves 3 steps. The SN2 reaction is concerted, means a single step. SN1 is the multi-step, stepwise 1 to 3. That is the same as summary here I am given here. The big barrier for SN2 reaction is steric hindrance, whereas the big barrier for SN1 is a carbocation stability. That is, here in SN2 reaction, you'll go for the steric hindrance. That is going to be the primary is greater than secondary, it is greater than the tertiary. Whereas SN2 reaction, in the case of the, see here, that's why the rate of the reaction proceed, primary is faster than the secondary, secondary is faster than the tertiary. This is for the what you call as the SN2. See, another big barrier is steric hindrance. This is sorry, carbocation stability. This is already I told you. Here the tertiary alkyl halides undergo what is called as the SN1 reaction and followed by secondary, so followed by the primary. For SN2, the rate of reaction increases going from tertiary to secondary. to primary alcohol halide. For SN1, the trend is opposite. See, for SN2C, primary is greater than secondary, greater than tertiary. And for the SN1, primary is less than the secondary, secondary is less than the tertiary. For SN2, the rate of reaction increases going from tertiary to, okay, the same here also. Remember that SN1 and SN2 reactions only occur for alkyl halides and related compounds like tosylates and mesylates. If the leaving group is directly attached to alkene or alkyne, SN1 or SN will not occur. You remember this. If the leaving group is directly present, alkene or alkyne, SN1 and SN2 does not occur, only for alkyl halides. The SN2 tends to proceed with a strong nucleophile. The SN1 tends to proceed with a weak nucleophile. Here, SN2 reaction for these are the strong nucleophiles, whereas methoxide, cyanide, alkyl sulfide, azide, hydroxide. Whereas SN1 reaction, this is going to be the methyl alcohol, water, sorry, methyl alcohol and ethyl alcohol and so on. The SN2 is favored by polar protic solvents, a protic solvent. SN1 proceed by a polar protic solvent. This is, you remember, SN2 is always APO solvents, aprotic polar solvents. That is DMSO, acetonitrile, DMF. That means they do not accept or they do not release the proton. Whereas in the case of SN1 reaction, it is a protic solvents like proton donor, water, alcohol, carboxylic acid, which stabilizes the resulting charged carbocation. When a stereoisomer is involved, in SN2 reaction provides inversion, whereas in SN2, SN2 you see this Walden inversion takes place. In the case of SN1, there is a racemization takes place. See, this is another URL you are provided, and here the animations are given in the YouTube. You can search with this URL. Thank you for watching this one, and we will meet with another one, that is a reactivity of allyl, benzyl, allyl halides. One more slide is there that we'll discuss in the next class. Thank you for watching this one. Okay, we will end this session. We will meet again in the tomorrow's class. Thank you for watching this one. And there is an examination at 8:30. Already heterocyclic compounds I already announced. Okay, see you in the next class.